are Hydrocat, Ankara University's hydrogen-powered vehicle group. We have been working under this name since 2006. We are designing and manufacturing new vehicles and competing in TÜBİTAK's annual efficiency challenge races. There are two categories in these races, electromobile and hydromobile category. We competing in hydromobile category as a team. The teams competing in hydromobile category must use hydrogen as a source of energy. The usage of fuel cell is one of the strategies for utilizing hydrogen energy. Fuel cells are also used in our vehicles. Fuel cells, as you may be aware, are systems that use hydrogen gas to produce energy. The desired voltage and current values can be obtained by connecting these energy metal plates in series. As a consequence of advancements in material science and electronics, fuel cells have developed into devices with small volume but high output. Since a result, fuel cells may be employed in research and development studies for ships, drones, and automobile technologies, as every gadget or product that arises in our environment requires energy. Now we will look at how fuel cells are employed in automobiles. As is customary with electric cars, batteries are utilized to propel the vehicle and supply the necessary energy. In addition to battery in electric cars, fuel cells is employed in the cars we have constructed. The fuel cell PEM proton exchange membrane type fuel cell we choose was used in the vehicle produced. The briefly mention the PEM type fuel cells. After the electrolytic membrane is mechanically lined up between two serial metal plates, the hydrogen gas is passed through the channels on metal plates, and this hydrogen gas is transmitted through the membrane in between two other electrolytic metal layers as ions. Since the electron cannot pass through the membrane, a potential difference occurs at ends of these metal layers. We convert the voltage generated by this potential difference to electrical energy and use it power the electric motor driver in vehicles. Using fuel cells has additional responsibility because the fuel cell cannot maintain continuous power. It requires systems such as sensors for safety consideration, such as gas pressure and temperature.
Well, I want to ask some questions about the fuel cells. Among the often asked questions is why we are working on fuel cell powered cars while electric cars have become so prevalent.
Because battery technology are continually evolving today, but their energy capacity is insufficient and their lifespan is short. In addition, high volume is required for the batteries to move vehicle. In contrast, fuel cells are small in size, produce high power, and have a long operation life. It's about 60,000 hours or 2,500 days. This can be said as 5,000 cycles or 1,826 days for Li-ion batteries. In addition, since efficiency values of fuel cell are currently estimated at maximum of 20 and 60 percentage, this is 99 percentage in batteries. It is thought that high efficiency can be rapidly increased from battery technology by still working on it. In addition, fuel cells act as nature friendly since pure water is discarded as a waste byproduct in fuel cell after energy is produced in fuel cells.
Well, the next question is it safe to utilize hydrogen gas in fuel cells? For example, in the event of a collision, how safe is the driver inside the vehicle?
Obviously, the driver, fuel tank, and fuel cell are separate from each other in vehicle we have produced. This prevents hydrogen poisoning, such as loss of consciousness, dizziness, or asphyxia, in case of hydrogen leak. Additionally, to account for possibility of an internal spark, The hydrogen gas within the car is transported directly to nature by opening an air duct from cabin's roof, which houses car's fuel cell and hydrogen tube. With recent breakthroughs in carbon fiber tubes, the tubes don't burst, and gas within is discharged straight into nature. Finally, to guarantee driver safety, hydrogen gas sensor within car transmits information about hydrogen gas concentration inside the driver's cabin, and any rapid changes are informed to driver.
Thanks for inform us, Guseino.
Thank you.
Ne demek? Bu arada
araya geçmiş. Okay, hello everyone. This is the third day of the conference. Now we are in the keynote speaker session now, which is called plenary session. So our first guest is Dr. Hasan Aksoy. I would like to welcome Dr. Hasan Aksoy. How are you?
Thank you very much, Erol Hocam. I'm fine.
So I will give some a bit introduction about you, and then we will have 25 minutes talk for you and 5 minutes for the questions. Hasan Aksoy has been working in energy sector for 15 years in major local and international energy companies. His experience focuses on analysis of power market and system, energy trading, portfolio management, as well as research for energy transition. Currently, Mr. Aksoy works as head of research, acting director of Shura Energy Transition Center. He received his bachelor's degree in mechanical engineering and then master's degree in energy department, mechanical engineering from Yıldız Technical University in Istanbul. He also holds an MBA degree from Galatasaray University. He will talk about today. His talk title is Priority Areas for a National Hydrogen Strategy for Turkey. So thank you very much. We would like to listen to you, Dr. Hasan Aksoy. So the stage is yours. Thank you.
Thank you very much, Erol Hocam. I hope everyone can hear me well, and also please let me share my presentation. Okay, I think everyone can see my screen. I can start my presentation. Today, I will present Shura Energy Transition study and analysis that was published on February. We conducted the analysis Turkey priority areas for a national hydrogen strategy together with Bilkent Energy Policy Research Center. We will go details soon, and also I'd like to show some slides regarding our ongoing hydrogen study. So please let me start first with what Shura Energy Transition Center is doing. Shura Energy Transition Center is a think tank focusing on support energy decarbonization in energy sector of Turkey, and also providing a transparent platform working for Turkey energy transition, providing fact-based, unbiased, and independent research and analysis, covering technology, economics, and policies, steering debate on Turkey energy transition. If you look at key messages in our study, we have seen building a local hydrogen industry is becoming an important energy strategy ambition of Turkey. Green hydrogen can have a potential of about 5% in Turkey energy mix, especially for hard to decarbonize sectors of industry, buildings, and transport sectors. According to our analysis, first order estimate shows 4.6 million ton equivalent oil per year green hydrogen potential exists. But in order to achieve this amount, we need 12 gigawatt electrolyzer capacity and almost 36 gigawatt renewable energy capacity, together with a total investment of $45 billion in, actually, this is total number, including a renewable power capacity. If you look at the priority areas for Turkey, developing a hydrogen strategy will be crucial with a clean plan with cost, benefit, and system implication of hydrogen production. And also we need to understand mobilizing, financing, understanding hydrogen business opportunities, including export potentials. And also we need to understand contribution to Turkey energy transition as a local resource. If you look at the countries, many countries published or released a strategy paper, roadmap, vision document, and also R&D programs. It is very hot topic, hydrogen nowadays in energy sector. Also growing number of studies undertaken by intergovernmental organizations that focus on clean energy sources such as International Energy Agency and IRENA. If you look at application areas of hydrogen in the energy system, three important areas exist, especially they are very hard to decarbonize. So one of them is transport. Fuel cell and electric vehicles are complementary battery electric vehicles, so we can use hydrogen there. And also rail, aviation, maritime sectors is another important areas for using hydrogen. And also we can use hydrogen industry, replace fossil fuel products. And also we can use feedstocks. We can use hydrogen for producing feedstocks, I can say. And also we can use or produce new commodities like ammonia. And also natural gas, another important sector. We have a chance to hydrogen blending in natural gas grid. So it will provide many benefits in terms of, especially, we are using natural gas in our buildings for heating and also cooking. So it will provide some benefits in terms of decarbonization in our building sector. And also natural gas blending in natural gas grid provides seasonal storage for solar wind integration, provides grid services, and also distributed stationary fuel cell for heat and power generation. If we look at Turkey total final consumption, it's around 109 million ton equivalent oil. It is 2019 figure, and our energy import dependency continues. So if we look at the sectors, what they are, their position in terms of energy consumption. If you look at power sector transformation, it is already going well. It is underway with a sense of, I can say, urgency and climate action. So in Turkey, almost nearly half of all demand is coming from renewable energy sources. Wind and solar share is almost reaching 15% share. So I can say energy transition is underway, but electricity share in total final energy consumption is around only 20%. So other sectors also important. I mean, the manufacturing industry, one of them is 39% of total final consumption. Turkey is within top 10 globally is steel production from electric arc furnace, and also cement is another important sector. Textile, food, machinery, and paper industry is also relatively large sectors. They are using mainly fuel-based products. And also another important point, we need to understand potential impact of a border carbon adjustments on Turkey industry competitiveness. So it is very important to make decarbonize in manufacturing industry in order to avoid any potential impacts from a border carbon adjustment. Buildings are large gas users, as I mentioned before, for heating and cooking especially, and growing rapidly. 31% of total final consumption belongs to this sector. So it is also another sector that's hard to be decarbonized. So transportation sectors also cover 26% of total final consumption. It is not easy decarbonize also this sector. Out of nearly 13 million passenger vehicles, only 2,000 and maybe 3,000 electric vehicles exist in Turkey. But Turkey government has a vision, the 2030 vision. We expect 1 million electric vehicles will be on road. But on the other hand, more attention is needed to transform other transport modes, road freight, and around 4.5 million vehicles needs to be taken into account. So, as I mentioned earlier, three main hard to transform sectors of Turkey represent around half of all final energy demand. One of them is manufacturing industry. The other one is natural gas sector and also a transport sector. They are cover almost higher than half of total energy consumption. They are also responsible for around 50%, 45% total CO2 emissions. Okay, let's see opportunities for green hydrogen in Turkey. Manufacturing industry is important area to decarbonize, and also we can replace foil-based products with hydrogen. Electric arc furnace route can be utilized further. It will provide less CO2 emissions as well. And production of synthetic fuels to decarbonize industrial energy use, especially cement, chemicals, petrochemical industries. Reviewing the ammonia industry and building a methanol industry can be taken into account. We can create this kind of sectors, or I can say industry. Another opportunities in the building, as I mentioned earlier, blending with natural gas, it will provide benefits as far as we know, 5% of blending region with actual field tests ongoing. So literature also says that it is possible to reach 15-20% blending in natural gas grid. So it will provide benefits. Transportation sectors, notably for road freight cars, fuel cells will be important. And power, if we look at power system, seasonal storage can be another alternative for wind and solar integration, especially. According to our analysis, we reach 4.6 million ton potential for, there is a 4.6 million potential for green hydrogen. If we split sectors, 2.1 million ton in industry, 1.8 million ton for road freight and transport, and 0.6 million ton for blending in gas grid. All of them, it is around or equal to 5% of Turkey's total final energy consumption. In, of course, this figure shows 2018 figure. So, in order to reach this potential, we need 12 gigawatt total installed electrolyzer capacity. We need also electricity supply almost 36 gigawatt from renewable energy resources. Totally, we can say total investment needs will be around 45 billion US dollar if we take into account the current technology costs and levels. You can see also segmentations below what sector will be needed hydrogen demand and also electrolyzer capacities. But on the other hand, hydrogen logistic and trade potential need to be understood in developing Turkey's hydrogen strategy with a country's significant potential of renewables, and also minimize grid investments and consumer on-site power to produce hydrogen needs to be mapping and needs to be done in strategic development. Supply locations, especially in our analysis, we investigated wind and solar potentials in Turkey. So supply locations should be matched with demand locations as well, where hydrogen will be used. Left side, you can see solar irradiation is the highest in central and southern parts. Wind also, right-hand side, you can see the graph. Wind benefits the highest output in the western parts. So in our next study, ongoing study, we will investigate also regional basis hydrogen potentials and also demand, and also we will see export potentials. So, yeah, as I mentioned earlier, I would like to show also our ongoing study opportunities for production and export of green hydrogen. We are conducting this study with Bilkent Energy Policy Research Center with support of the German Energy Agency. So aim of this study, assess Turkey hydrogen market development potential, assess location for suitable plants for production of hydrogen, and assess export hydrogen potential and its derivatives in the near term and medium term. Probably we will plan to release a report in September 2021. If we look at the methodology steps in this study, we will look at between 2050 based on level of 81 provinces in Turkey. We'll assess technical supply potential of green hydrogen, cost of hydrogen production, a brief assessment of hydrogen demand in Turkey from gas manufacturing industry, transport and power sector users. And finally, I will identify the export potential and suitable areas of green hydrogen through pipelines or inform end products such as ammonia and methanol to European Union countries. We assessed two scenarios in this study. One scenario, decentralized. Hydrogen production is determined after taking into account water stress for each province. Hydrogen is first consumed in priority sectors, province-based, and also remaining hydrogen transferred designated regions for export via hydrogen pipelines or blending in natural gas pipelines for direct export. In designated regions, hydrogen is converted to end products, ammonia, and exported. It is also another alternative. Second scenario, centralized. We created six designated regions after accounting for water availability. Hydrogen is first consumed in priority sectors at the designated regions. Remaining hydrogen blended in international gas pipelines for direct export or converted to end products like ammonia and exported. So, of course, if we choose these six designated regions, we created index like port availability, industry, refineries, renewable proximity, water resources, demand centers, infrastructure, this kind of.
Dear speaker, last 5 minutes, please.
Thank you very much. This is my last slide. I would like to mention our study results, what we reached. Understanding opportunities of green hydrogen to reduce energy import dependency. Understanding the opportunities for the gas sectors using, mobilizing financing for electrolyzer and renewable power capacities. We need to plan for renewable energy integration to green hydrogen production. We need also understand cost, social, economic, and environmental benefits of hydrogen production, including business opportunities and exports. And we need to understand power system implications of green hydrogen. We need to create a hydrogen ecosystem. And finally, it is maybe most important part, positioning the role of green hydrogen in Turkey overall energy transition strategy. So my presentation finished. Thank you very much for listening to me. If you have any question, I can try to answer. And also you can directly email to me. And you can also find detailed report in our website, Shura Energy Transition website. So thank you very much.
Okay, thank you very much, Dr. Aksoy. So we are ready for questions. We can get a few questions if you are interested. You can make unmute yourself and you can ask. From chat up to now, I do not have any question, but of course you can speak and ask question. Okay, maybe I can ask one question, maybe for your personal interest. I mean, what do you think after 10 years in Turkey, what can be the percentage of hydrogen energy usage when we compare with other renewables? I mean, including wind energy, solar energy, photovoltaics, and so on. So just for your personal estimation rate, I'm asking. Thanks.
Yeah, thank you very much for your relevant question. Of course, it is not easy to answer this question because if we think 2030, it's quite close date. So currently we don't have any green hydrogen production, as far as I know. Maybe a minor amounts can be exist, but overall I can say we have great potential in renewable energy sector. As you know, we have great solar and wind potentials. So I believe that in Turkey we need produce green hydrogen with purpose of blending in natural gas grid, because it is already test ongoing. So 5% of blending already succeeded, as far as I know. So it will provide nice many benefits also, decarbonize energy sector. So my first estimation, probably we will use hydrogen in gas grid for purpose buildings, and also maybe natural gas power plants. So yeah, I can answer just maybe 5% of total.
Are there any other questions? Okay, probably there is no other question. So thank you very much again, Dr. Aksoy, for this interesting talk. Now we are skip to other invited speaker, keynote speaker, Professor Muhammad Hasan Sayat. So I think he is here. Professor Sayat, are you here? Okay, very good, very good. So I will give some introductory information about Professor Sayat. Actually, his biblio is very long, so I would like to somehow give some short form. He is working as a member of Faculty of Engineering Sciences from GIK Institute of Engineering Science and Technology in Pakistan. Professor Sayat received his master degree in physics with specialization in electronics in '83 from Government College University in Lahore, which I have been there a few years ago. A very nice city. Professor Sayat is a recipient of PAC US and PAC China Research Awards, in addition of several other national and international research awards. He is serving the GIK Institute since the 1st September 2002. Since 2009, he's professor at the faculty. Professor Sayat's research interests are in the areas of computational modeling of electronic structure of atoms, molecules, organic electronics, I cannot see, okay, photonics, energy harvesting technologies, amplified stimulated emission and laser ablation. He made great contributions, especially to the strengthening of research and development activities in Pakistan. And he worked and supervised several master and 13 PhD students in multidisciplinary areas. He established international collaborations, especially with the South Dakota State in US, University of Malaya, University of Auckland, Virginia Tech, Cambridge, Brown State University, and McGill University. Currently, he is conducting research on the dye-synthesized solar cells, quantum dot synthesized solar cells, and organic ones. So thank you very much to join us, Professor Muhammad Hassan Sayed. And we would like to listen to you now and for your valuable studies. Thank you. This stage is yours. Yeah, please.
Bismillahirrahmanirrahim. Mr. Chairman, thank you for providing this opportunity. And I am thankful to Professor Yasmin and her team
Nice to
on
meet you.
leading this excellent event. So outline of my talk would be brief introduction of myself, faculty and institute, solar energy harvesting activities in Pakistan, and why perovskite solar cell, architectures and designs of perovskite solar cell, design, fabrication, working and characterization and simulation of whole transport material free monolithic perovskite solar cell. And then I will be sharing some of the results we have recently published. And then a few slides would be about a new approach, which is using a laser ablation for providing ultra-fast heat treatment of different perovskite films, because in the fabrication of perovskites, we have to deposit different films and then provide heat treatment to those, and it takes a long time. But this laser annealing is ultra fast, and these systems are now becoming very common and their prices are falling. And then conclusions, acknowledgement, and a few references at the end. So I will be just, so my PhD was about probing of excitation, de-excitation of atomic and ionic species isoelectronic to sodium, magnesium, aluminum, and silicon sequences. And the study was carried out using a time-synchronized dual laser plasma, using a photographic and imaging spectrometers, and recording of time and space resolved spectra were carried out, as this one is shown as temporal recording of photoabsorption spectra of silicon, neutral, and singly ionized. And then interpretation was provided based on computational modeling of atomic structure using multi-configuration, Dirac-Fock and Hartree-Fock packages. So since 2002, I have been at the GIK Institute, and we started here because it was not possible to have that facility here. So we then started with liquid batteries, then moved to junction diodes, Schottky diodes, heterojunction, employing organic semiconducting materials synthesized in the country. And then we worked on sensors using organic semiconducting families of azodides, porphyrins, phthalocyanide, synthesized by groups of chemistry within the country. Then use the same materials for photo detection, making organic field effect transistors, organic memories, and amplified spontaneous emission studied in crystalline polymers. Then moved to solar cells, and currently we are mostly working on solar cells. And then in these areas, the students who did PhD under me, they are shown here. This did on sensors, these did on photo detectors and organic field effect transistors. These did on solar cells. And then these did on amplified spontaneous emission. And this one on sensors. And then these three did on recently on solar cells. One is doing postdoc in China. So that's the our alumni and collaborators. So my collaboration is mostly with the groups from chemistry. They are synthesizing the organic semiconducting materials, and we are involved on their characterization for electronic, electric, electronic, and photonic devices. And these are our collaborators from Department of Electrical and Computer Engineering from South Dakota State University. This one was from Libya, and this was from Iraq. They are doing, that was doing a PhD, and this I think was doing postdoc there. So we have very active groups. These are the students which I have recently supervised in MS and PhD, and some of our collaborators from different departments within the country. So that's my first PhD student. We at the Faculty of Engineering, GIK Institute, are running undergrad and graduate programs. In undergrad, we are running an engineering degree called BS in Engineering Sciences with specializations in photonics, modeling and simulation, semiconductor and microelectronics. So it is same as electrical engineering, but we have 5 specialized courses and 2 labs which are related to these specializations. So we are the only in Pakistan running this specialization. In graduate level, we are running the programs of applied physics, applied math, photonics engineering, digital system engineering, both at MS and PhD level. Recently, we have constructed a building for starting a department of photonics engineering, and that's the processes of its accreditation is ongoing. So we have these organic electronics and photonics research labs. Recently, under the PARC-US project, we have established 4 labs related to photovoltaic research. These are about the fabrication, characterization of solar cells. We have this facility for recording transient photovoltage and photocurrent facilities, which is using a pulsed NDR laser and storage oscilloscope. And we have also facilities for the computational modeling of electronic structure of molecules. We are close to a very big hydroelectric dam called Trebela Dam. The lake is only about 3 kilometers behind our that residential area. We have these houses, and behind that is the lake, and we are from 3 sides we have small mountains. And I have been teaching mostly courses related to photonics since 2002, and just having a class of about 8 to 9 students. And every year, 2 to 3 students have been going for PhD in photonics. From this class, 3 have completed PhD in photonics and they are abroad. So we started solar cell research by using these different fruit extracts and used these as energy harvest absorbing materials in dye sensitized solar cells. And first I gave final year projects to undergrad students, and they made solar cells using these fruit extracts and compared with the champion cell made with the N719 dye as a sensitizer. So that was the work which was presented in open houses. It was presented in April 10 to 11 2014 open house and industrial fair conducted at the GIQ Institute. In one of the cells, we used nanoparticles of silver mm, made using laser ablation. So these were the final year projects which I conducted, supervised from 2012 to 13. Most of these students have done PhDs. This group of four, they belong to the same class. They have done PhD in photonics, and they're working in Belgium and Finland. This girl did PhD from Turkey, and she is there. So why solar energy? Solar energy is an unlimited form of clean and renewable energy that's abundantly available in Pakistan. The solar energy that hits the planet in 1 hour is equal to the total amount of energy consumed by all human activities in a year. Cost-effective harvesting of solar energy can endlessly fuel our civilization. Located in the Sun Belt, Pakistan is an ideal place to harvest solar energy. With just 10% efficient solar cells, the sunlight that illuminates 0.5% of Balochistan province of Pakistan, which is the largest in area but smallest in population, would be sufficient to meet the energy needs of the entire country. So recently there is a boom of utilizing solar energy in Pakistan because the cost of electricity supplied by the government is very high, so people cannot afford. So everywhere, on every roof, one can see in Pakistan that people have installed solar cells. And some people, even they haven't been in school, but they know how to use a solar technology. They can buy solar panels which are available all over the Pakistan, in villages and cities, everywhere. One can buy the solar panels and inverter and batteries, and they can assemble without any help. So you can see people here, they are sitting and they are enjoying solar cell technology. This is a solar tube well, and in Pakistan, there are now people running full days and paying nothing. And in every institute or department, people are now installing the solar cells. And there is a one university which have inaugurated the recently installed solar cell facility. So there is a lot of opportunities for solar technologies in Pakistan, and there are many companies and expertise available. Next generation solar cell technologies comprise these dye-sensitive solar cells, organic photovoltaics, quantum dot solar cells, and perovskite solar cells. And we have been working on all these. So this is the old slide, but you can see the evolution of the performance of solar cells through the years. So the efficiency of DSC increased at a very slow rate, and it has been around 14 for many for past about 1.5 decade. And then bulk heterojunction polymer solar cells, though its efficiency hasn't exceeded 50%, but lot of printing facilities have been developed, and now it is possible to print like a newspaper these bulk heterojunction solar cells by buying the roll-to-roll slot die-coated printers and commercially available inks and plastic substrates. And the efficiency of perovskite solar cell started from 4% and has gone above 25% in 2021. And the advantages of these technologies over others are because they are alternative to silicon, they are solution processable, they can be fabricated easily without having costly equipment. and manufacturing processes transfer to industry. So these are the different architectures, designs of perovskite solar cell. One is this one where people start with the glass electrode and with the fluorine tin oxide coated on that. Then a thin film of compact titanium as electron transport layer is used. Then there is a mesoporous layer of titanium, and then there is a perovskite layer, then there is a whole transport layer, and finally gold or silver are used as metallic electrodes, but that's expensive. So these are the different architectures which people are commonly using, and they are playing with different materials, are using new materials, new perovskite materials. So there are a lot of opportunities for every discipline, like for people of chemistry, researchers of physics, electronics, material sciences, mechanical engineering. We have recently been working on the fabrication, characterization, optimization, and simulation of full transport material-free perovskite monolithic solar cell. And many companies are providing prefabricated different at to different levels of this technology. Like one can buy prefabricated glass, FTO, titanium, zirconia, carbon electrode, and then they can infiltrate perovskite and provide heat treatment, and the cell is ready within about 1 to 2 hours. They can coat their own layers, they can try different mesoporous layers, different these spacer layers, and then they can work on optimization or conductivity enhancement of these carbon electrodes, and they can try different perovskite precursors. So there are a lot of things commercially available. So these are the different layers of that which are mostly FTO glass is available, but it has to be etched either chemically, or mostly people are using lasers for making these monolithic electrodes. And the other layers are screen printed. So that's the schematic of this monolithic perovskite solar cells. So we are working on fabricating different layers, and also we buy these prefabricated electrodes. They are heated to 450 degree, and then this perovskite precursor is heated at about 70 degree, and then it is infiltrated and dried for different temperatures to optimize its properties. And you can see that there is a groove, or these two electrodes are isolated electrically, insulated, sorry, and using a laser. So if one has laser, then they can do otherwise. So these are commercially available from many places. This device is known as a whole transport material free carbon-based monolithic perovskite solar cell. And it is because in the earlier designs I have shown, a sphero was used as a whole transport material, but that's expensive. And also they need deposition of gold and vacuum thermal evaporation is needed. So the technology is not scalable, but that's whole free and easy, and also it is scalable and printable. Every layer is printable. So it can be mass produced once its efficiency is enhanced reasonably, and its stability issue is resolved. So that's the energy level of this. The light is absorbed by the perovskite layer, and then separation of electron and hole takes place. Electron is moving, falling to that conduction band of titanium, and then falling to FTO, and then flowing in the outside circuit. Their energy levels are also given in this slide. And these are the fabrication processes which are used. So you can see that we start with this prefabricated monolithic electrode, heat that at 400 degrees Celsius for 30 minutes. Then a polyamide adhesive is applied to avoid spreading of the precursor. Then the precursor is dropped at, we allow it to infiltrate. Then it is heated about from 50 to 110 degrees. It depends upon the precursor and the solvent used in that. So optimum temperatures are different for different precursors, but they range.
Dear speaker, last 5 minutes.
So that was the software freely available which we have used for simulation. I will be just sharing results of this first one, impact of heating temperature. So we have heated the perovskite film at temperatures of 50, 60, and 70 degrees Celsius. And the optimum performance was obtained corresponding to heating of 60 degrees Celsius. And the paper has been published recently about the impact of drying temperature on photovoltaic performance and impedance spectroscopy of whole transport material free air processed perovskite solar cell. It was done as part of MS thesis of my students. And these are the results. You can see from the IV data that at 60 degree, the performance is highest. So we confirmed this on the basis of IV and CV studies where more Schottky analysis was carried out to show that the performance is highest at 60 degrees Celsius. So that's the table showing comparison of the photovoltaic performance at 3 different temperatures. And that was the impedance spectroscopy we carried out to compare that and provide charge transportation enhancement. Then recently we have carried out another study about hysteresis analysis. So the photovoltaic parameters depend largely on the sweep direction and sweep delay. And there is a lot of hysteresis found in that. That you can see here that in the forward sweep, you can see that the results are, the performance is very low as compared to the reverse sweep. That was the hysteresis we studied in the impedance spectra of this device. There was another study carried out using a different precursor concentrations. So we were able to find highest performance corresponding to precursor amount of 5 microliter. And that's the impedance spectra we carried out. Now, we have also done simulation of that, and using semi-empirical approach by using the actual values of series and shunt resistance, we were able to simulate results in a very good agreement with the measure this one. So you can see that the simulator and experimental results are in a very good agreement if the actual values of series and shunt resistance are included, and then other values are optimized, like thickness of the films and the band gap of the perovskite. Now that study was taking a long time. Recently, papers have been published on ultra-fast laser annealing, where the laser line beam is scanned over the film, and the temperature is optimized using this thermal imaging camera. And here you can see that annealing has been carried out using three different laser diodes and conventional ways. So that is a convention, that is done with the laser diodes of 500 nano, 400 nanometer and 450 nanometer. You can see that the annealing carried out at 450 nanometer is better, showing a larger grain size. And then the spectra, these films were used in the fabrication of these perovskite solar cells. You can see that using a laser diode at 450 nanometer, the results are better than made using a thermal annealing with
Dear
conventional
Professor,
method.
I think the time, okay. Now for the conclusions,
I
we can
have
get
just
into
finished, please. Thank you.
Okay.
Thank you very much.
Okay, so thank you very much for this interesting talk. So we are now in the question stage. There are some questions here I see. For instance, one question says that, what do you think hybrid system which connected to solar cell to produce hydrogen energy, for example, solar cell, electrolyzer, and PEM fuel cell?
Well, for electrolyzer, every solar cell technology can be used. Like I gave a final year project, we bought electrolyzer and a fuel cell at undergrad level. So we have been using a silicon solar cell, but these silicon solar cell technology fabrication is not in every country. Like we in Pakistan don't have a silicon wafer fabrication or solar cell. And these third generation solar cells, they are solution processable, and any country willing to fabricate or establish industries would be able to do that because no large expertise is needed. So we just need, printers are reaching within market, and just buying a few inks substrates and synthesizing some things locally. Every country can start solar cell fabrication, and they are used in like hydrogen generation using electrolyzers. And also they are printable, and they are finding a large scope in these IoT applications. Like we have carried out one study in that we have examined influence of laser light irradiance for applications in IoTs.
Okay, thank you. Another question from Professor Ikmayes. Is there solar cell industry in Pakistan? She asks.
We have assembly plants, like one I have visited a plant, but he is making concentrated solar modules, but he is selling abroad because they are very expensive, and in Pakistan no one is interested in that. So he is selling. So we have a lot of fabrication plants, but not fabrication of silicon crystals. So
Okay.
that we are buying from other countries. Mostly we have a Chinese made, and but we have plenty in Pakistan, because I think in the near future I also have constructed my new house, and planning to install a solar cell facility on that. So it is because of the high prices of the electricity from government. So everyone is now shifting towards solar.
Yeah, a few years ago when I was in Pakistan, I have recognized that there is some governmental issue that they are trying to build new plants or factories to produce solar cells also, domestic solar cells. So I know that Pakistan is now on the way to produce photovoltaics mostly.
Yeah, yes, we are also developing a facility for the printing of these perovskite solar cells.
Yeah, thank you very much.
We are now trying to buy some printers because some years back, the price of the roll-to-roll printer was about 6 million Pakistan rupees, but now that has fallen down to about 1 million.
Okay, very good. Thank you very much, Professor.
Thank you.
Yeah, now we are going to the, yeah, are there any other questions? Any questions? Okay, maybe, so we can go to the third presentation now. Now I would like to introduce Professor Shadiye Ikmayes. She is one of my colleagues also for past years. We have been collaborating for many times. I welcome her here to be in this valuable conference. I will give some small introductory about her. Professor Ikmayes had received her BC and Master from the Physics Department in the University of Jordan in 83 and 87 respectively, and PhD in producing CDS and CDT thin film solar cells from the same university in 2002. His research is focused on producing and characterizing semiconductor thin films and thin film solar cells. Besides, she works in characterizing quartz in Jordan for the extraction of silicon for solar cells and characterizing different materials by competition. She published 60 research papers in international scientific journals, 85 research papers in conference proceedings, and 3 chapters in books. She is the founder and the editor of book series Advances in Material Research and Technology, published by Springer, and the editor-in-chief for several books. She is also a member of Minerals, Metals, and Materials Society, TMC, where she was the chair of the Characterization Committee of TMS 2016-17 and the leading organizer of 3 symposiums. Also, she is a member of the World Renewable Energy Network Congress and also a member of the International Organizing Committee and the International Scientific Committee in one of my events, the European Conference on Renewable Energy Systems. She is a guest editor and a member of the editorial board of several journals, including Journal of Materials and the Journal of Electronic Materials. She is a reviewer in 24 international journals and several international conference proceedings. So you are welcome, Professor Ikmayes. Now, today we will listen her talk about photoluminescence spectra of spray deposited CDS thin films. So please take your talk.
I will share a screen.
Thank you. Yeah.
Good morning, everybody. As the chairman said, the title of my presentation is Photoluminescence Spectra of Spray Deposited CDSIN Thin Films. Here is the list of contents of my presentation, and this is also part of the contents. Now, the motivation. Cadmium sulfide is an important 2,6 compound semiconductor which has high efficiency that makes it of potential use in several applications in photonic and optoelectronic devices. The band gap of cadmium sulfide is about 2.48 electron volt at room temperature. This band gap is good to make it suitable for different industries in photonics and optoelectronics. Cadmium sulfide nanoparticles and nanostructures are used for several applications such as optoelectronics, photocatalysis, solar energy conversion, and photodegradation of water pollutants. The introduction. Cadmium sulfide is a wide band gap semiconducting material. It represents two phases, cubic, zinc blende, and hexagonal wurtzite structures. But the wurtzite structure is the stable one. It has a direct band gap of value 2.57 electron volt at room temperature. The cubic one is metastable and it has a lower band gap energy of 2.4 electron volt at room temperature. Thin films of CDS has several applications, especially as window layer in heterojunction solar cells. Cadmium sulfide is N-type material due to its intrinsic sulfide vacancies, sulfur vacancies Vs. However, to use it as window material in heterojunction solar cells, the N-type conductivity of this material can be or must be enhanced, which can be achieved by several ways. From these ways, the variation of the reagent precursor concentration or doping with cationic atoms such as indium, boron, and silver. In this work, we used indium as an intentional dopant to produce thin films of cadmium sulfide. The crystalline quality of the semiconductor film can be analyzed by means of photoluminescence. The photoluminescence is a sensitive technique and it is non-destructive optical technique. Photoluminescence can provide information about impurities in materials and defect centers which act as recombination centers for charge carriers, which also reduce the photovoltaic conversion efficiency. Cadmium sulfide has intrinsic defects. Most of them are dominant donors, and one of them is deep acceptor. From the donors is sulfur vacancy shown here in the schematic. It is above Fermi level in the conduction band. Cadmium interstitial, which is close to the bottom of the conduction band, so it is a shallow donor. Then cadmium empty site, but it is less favorable, and sulfur interstitial, here it is in the band gap above the Fermi level, and it has dominant native acceptor which is VCD, and it is deep acceptor as shown in the schematic. For the use as window layer in solar cells such as CDS, PL probes optically active recombination centers. Some of these recombination centers contribute to losses in photocurrent of solar cell devices due to optical absorption in the CDS cadmium CDS window layer. So the intensive study of the photoluminescence of cadmium sulfide as bulk or thin films is very important for the use in solar cells. Usually, the PL spectrum of cadmium sulfide shows three peaks. They represent bands. One of them the sharp band in the green-yellow region, then a broad band in the yellow region centered at about 600 nanometer, and it is attributed to surface defects. Then a weaker band in the infrared region centered at about 1100 nanometer, and it is due to native defects such as sulfur vacancies and cadmium vacancies. Due to using thiourea and cadmium chloride, there will be another defect. It is It is known as CLS, which means chlorine replaces sulfur in the crystal lattice. Also, due to using indium as a dopant, there will be a shell donor near the bottom of the conduction band, and this is good because it is used to increase the conductivity of this material. By studying the dependence of the intensity of the photoluminescence on incident laser power and sample temperature, it is possible to make deductions about the physical nature and chemical origin of these emissions. Cadmium sulfide thin films can be produced by several methods: thermal evaporation, chemical vapor deposition, chemical bath deposition, RF sputtering, electrodeposition, pulse laser deposition, screen printing, and spray pyrolysis method, which is used in this work. It is used in this work because it is an easy method and it is simple, where no vacuum is used, no sophisticated equipment, and it is not expensive, and it enables intentional doping and the production of transparent and large area thin films. Now the experimental procedure. Cadmium sulfide thin films were prepared by the spray pyrolysis using thiourea and cadmium chloride dissolved in distilled water. Indium chloride is used as the source of indium. The solution was spread intermittently on hot glass substrates, and the microstructure of the films was examined using X-ray diffraction and scanning electron microscopy. A Philips PW1840 compact X-ray diffractometer is used, where CUK alpha line is used to get the diffractograms. FEI scanning electron microscope that supports energy dispersive spectroscopy apparatus is used to get SEM images and compositional analysis. PL spectra are recorded using air product cryostat that enables cooling down to 10 Kelvin. Argon ion laser of wavelength 488 nanometer is used as excitation source. Multi-channel optical spectrometer Avantas fiber optic is used to collect the laser signal, the PL signal, and it has two gratings. The first one covers the range 640 to 1280 nanometer, and the second grating covers the range 190 to 860 nanometer. Here are the results and discussion. First, the microstructure and compositional studies of the spray deposited CDS thin films. Here are two diffractograms for two films, one of thickness 500 nanometer and the other of thickness 140 nanometer. As you see in the diffractograms, the films appear polycrystalline, and they show mixed phase, cubic and hexagonal phase. Now the symbol C refers to cubic, C refers to cubic, and H refers to hexagonal. Now in this figure you see SEM images for the same two films. This one for the thicker film, and the average grain size here is about 200 nanometer, and this one for the thinner film, and the average grain size is about 100 nanometer. Here are the EDS spectra for the two films. The films contain cadmium, sulfur, and indium. Now the ratio of cadmium to sulfur in this film, which is the thicker film, is 51.05 to 46.98 atomic percent, or 1.09. This means this film is CD rich. The ratio of indium to cadmium in this film is 1.97 to 51.05, or 3.86 atomic percent. Now the thinner film, the ratio of cadmium to sulfur in this film is 46.97 to 49.75 atomic percent, or 0.94, or this film is S-rich. The ratio of indium to cadmium in this film is 3.28 to 46.97 or 6.98 atomic percent. So this film, the thinner one, has less cadmium but more indium, so it will balance, indium will balance its n-type conductivity. Now this figure shows the PL signal or PL spectra of the same two films which are here as deposited. You see the red line for the thicker film and the black line for the thinner film. Now here in part A, the broad band which represents yellow-red bands, and in the other one, this band is the infrared band. Now the yellow band is centered at about 2.057 electron volt for the thicker film and 2.064 for the thinner one. The infrared band is centered about 1.067 electron volt for the thicker and 1.063 for the thinner one. As you see, the photoluminescence spectra has higher intensity for the thicker film but lower for the thinner. And you see there is a structure and sharp peaks in the PL spectrum of the thinner film, and this is due to the presence of nanoparticles, because as I mentioned before, the grain size, the average grain size in the thinner film is about 100 nanometer, which means there will be effect of this nanostructure on the PL spectra. Now a deconvolution peak FET was performed for the peak in the yellow region, which covers the red and yellow bands, and the spectrum is fitted to Gaussian peaks. We get 13 peaks after the FET. Now the positions of the peaks is confirmed by evaluating the second derivative, where, as you know, the position of the peak is at the minima of the second derivative. Now we see here the center of the yellow band is at 2.0236 electron volt. Now another peak FET was made for the part in the red and infrared region, and as you see here, the sharp peaks which are related to the presence of nanoparticles. Here you have the infrared region and the tail of the red region. When this is fitted to Gaussian peaks, it gave 44 peaks. And also the second derivative was used to confirm the positions of the peaks, where the positions are recorded on the figure. Now, as you see, the sharp peaks, when fitted, they give doublets here, doublet, etc. We see doublets everywhere. These doublets are related to the presence of two phases in the films, the cubic one and hexagonal one, where they are separated in energy by about 6 to 7 milli-electron volt. Now, this FET shows bands, and we have 7 bands. The peaks are collected in bands, and the number of these bands are 7. 2 of them are in the red energy, tail, the tail of the red band, and 5 of them in the infrared region. The strongest one is this one, and it is in the range 1.82 to 1.9 electron volt. It contains 5 peaks and 1 doublet. This peak or this band is related to sulfur vacancies near the center. Now the next strongest peak is the next strongest band is this one, which extends in the range 1.72 to 1.82 in the near infrared region, and it consists of 6 peaks and 2 doublets. Now the effect of annealing in nitrogen atmosphere and HCl etching is studied. As we know, the thermal annealing in different atmospheres induce changes. These changes include changes in resistivity of the films, interplanar atomic distance, and band gap energy values. Etching, as you know, removes the surface layer. In our case, it is most probably cadmium rich. The removal of this layer decreases a complex known as ICD-VCD, and removal of this complex makes the films more ordered, and then it encourages the change from mixed phase to hexagonal phase. Now here the PL spectra of two films, for one film before annealing as deposited and after annealing. So the black spectrum is for the annealed film, and the red spectrum is for the same film before annealing. As you see, the photoluminescence signal was quenched or decreased, its intensity decreased after annealing. You see this shoulder in the red region had approximately disappeared after annealing, and in this part you see the red tail. The shoulders in the red tail approximately disappeared after annealing. These PL spectra are taken at temperature 23 Kelvin of the sample. Now also you can see that the center of the band is shifted after annealing, and we have a blue shift here, the as deposited, and here the annealed. Also in the infrared, the center of the infrared band is blue shifted. Now here deconvolution for the PL spectrum obtained after annealing. We got 11 peaks, and also the second derivative was found to confirm the position of the peaks. As you see, the position of the yellow band, now blue shifted, it is 2.0594 electron volt. Here a comparison between as deposited and annealed film. You see the number of peaks is decreased from 13 to 11, and the peaks corresponding to the red shoulder in the red region disappeared. Here the PL spectra of HCl edged film and annealed film. You see the shoulder is removed approximately, and you see the effect of annealing is stronger in removing the shoulders in the in the red tail. But the effect of annealing is stronger than the effect of etching. Now here a comparison between as deposited film, annealed film, and HCl edged film. We see the number of peaks is decreased after annealing and etching, and a blue shift of the peaks has occurred in both cases. Now we study the effect of sample temperature on the PL spectra for all bands, and for intensity, position, and full width at half maximum. Here the PL spectra at different temperatures from 24 Kelvin to 160 Kelvin. You see the PL intensity decreases with increasing sample temperature. This occurs in the whole energy range for A and B in the figure. Now the decrease of PL intensity with temperature can be explained by this formula, which relates the intensity of the photoluminescence with absolute temperature. In this relationship, I0 represents the intensity at 0 Kelvin, A is parameter, K Boltzmann constant, EA is the activation energy. Now the exponential factor in the denominator, when the temperature becomes high, it becomes closer, it becomes larger than 1, and 1 in the denominator can be neglected. Now, a deconvolution peak FET was made at every temperature for first the peak, which includes the yellow and the red bands. It was deconvoluted to two peaks. One represents the yellow band and the other represents the red band. It is done for all temperatures. The FET parameters are inserted in these tables. This table for the yellow band and this table for the red band. It includes integrated area under the peak, center, full width at half maximum, and height. Also, the same thing is done for the infrared band, where it was fitted just to one peak, and this is done for all temperatures. The FET parameters also are shown here for this infrared band: area, center, full width at half maximum, and height.
You have 2 last minutes.
Okay, now integrated in area is plotted against temperature, and you see the decrease in integrated area with temperature for the 3 bands. Now, as I said, the exponential factor becomes larger than 1, and here we got this relation. Then a plot of the natural logarithm of the intensity against reciprocal temperature is performed. This is known as Arrhenius plot, from which the activation energy was evaluated. It is found in the 20s, and this means these bands are related to bound excitons. Now here the peak positions with temperature, as you see the relations, and the full width with temperature also are plotted. Now we come to influence of laser power. Here the PL spectra at different laser powers. As you see, the PL intensity increases with the laser power, and asymmetry of the yellow-red band increases with laser power. These are the relationships between integrated intensity and laser power. Here, increase, then decrease, then increase. It was approximated by power law, and a logarithmic plot was performed from which the slope was obtained. The slope was found to be close to 2. This means that these bands, yellow, red, and infrared, are related to bound excitons as obtained from activation energy. Here the plot of the center and full width at half maximum with laser power. Conclusions: 2 broad peaks were obtained, one asymmetric in the yellow-red and one asymmetric in the infrared. They are deconvoluted to Gaussian peaks. Intensity of laser decreases with etching and annealing. Annealing and etching have approximately similar effects. These treatments remove most of the defects, and a phase change from mixed phase to hexagonal phase occurred after annealing and etching. A blue shift of some peaks occurred after annealing. Arrhenius plots used to find activation energy. Now, spectral positions are found to be temperature dependent. Full width maximum also depends on temperature. The intensity of all bands decreased with temperature. A quadratic relation was found between PL intensity and laser power, which means that these bands are related to bound excitons. The decrease is related to laser heating, decrease intensity related to laser heating. Now, thank you for your attention.
Thank you very much for this interesting talk, Professor İkmayes. It's nice to hear in this conference. So we have one question, I think. Dr. Yeşim Molkoç, please, you can ask your question.
Hello, everybody.
Yeah.
First of all, congratulations for the work. However, I think the EDX analysis maybe should be revised because, according to the figure, cadmium in the left panel is not visible enough. I mean that the energy dispersion X-ray analysis. Can you show us again, because As far as I recognize, there will be something's wrong and going wrong. Maybe it can be checked again, I don't know. And also in my other question, was there any oxidation during these studies?
Sorry, I didn't understand the questions.
Okay, can you show us the EDS analysis?
What?
Energy dispersion X-ray analysis. You showed us after electron microscopy analysis, SEM image.
You mean this one?
No, EDS ones.
This one?
No, X-ray analysis.
X-ray, yeah, this one. Yeah.
After this figure, yeah. No, it was an EDS analysis, I mean, not X-ray diffractometers.
This is X-ray diffraction.
Yes, I mean EDS analysis, energy dispersion X-ray, the EDS one. EDS, after this maybe or before?
After, I have X-ray diffraction and SEM.
Yes, after two slides later?
This is EDS.
No,
Energy dispersion.
SEM.
Energy dispersion.
Yes, this one. Yes, that one.
Exactly
that one. Okay. As far as I recognize from here, you have indium as well, and also an S, but cadmium is a little bit in here. And which branch it comes from? An S? Yes, here.
Yeah.
These are only cadmium and S, right? And indium and cadmium proportions. But I mean that there will be an oxidation also and another kinds of, for example, the carbon.
But the instrument didn't find them. Just these found in the samples.
Yes.
If there are such elements, they are traces and cannot be detected by the instrument. You see it?
Only yes, I saw. Only K branch comes from here, right? Only K ones. M shells, I mean. The electron shells, I mean. Only K branch comes here.
Just we found cadmium, sulfur, and indium. No other elements.
Oh, okay. And another question that, okay, you also answered that. Thank you.
Okay, thank you.
Okay, thank you very much. Are there any other questions? Okay, then thank you very much for your interesting talk, Professor İkbayeş. Now we can go to the next presentation today in keynote speaker session. Professor Mohd Hazmizam Razali, I think he's here. Yeah.
Thank you.
So welcome, Professor. So I will give some short introductory for you. Professor Razali has a PhD degree in materials engineering from University Science Malaysia, master in chemistry and basic science in chemical industry from University Technology Malaysia. Currently, he is an associated professor at Faculty of Sciences and Marine Environment in Malaysia. He has published more than 50 technical papers in journals and conference proceedings locally and internationally related to the nanomaterials and functional materials research, owing to their significant impacts to the science, economy, and society. His innovative research and inventions have attracted global and national interests, enabling him to secure financial support from both private and government agencies. He has been awarded Who is Who in the world for 3 years, and for the Cambridge Biographical Center listed him as one of the 2000 outstanding intellectual of the 21st century. On top of that, he is also the recipient of the Mashiba Award and Geneva Gold Medal Award in 1999. Research interests mainly focuses on functional nanomaterials for renewable energy generation and biomedical applications. So today our speaker will talk about the hydrogen gas production through water splitting reaction using TO2 nanotubes for photocatalysis. So thank you very much. It's your turn, Professor.
All right, thank you to Mr. Chairman, Prof. So can you hear me?
Yes, yes, everything is okay.
All right, thank you. So, all right, okay. First of all, I would like to take this opportunity to thank the organizer for this, opportunity to present my paper in this conference, International Hydrogen Energy Congress and Exhibition. Earlier by Mr. Chairman, my title of research is hydrogen gas productions through water splitting reaction using titanium dioxide nanotube photocatalyst. So before we go detail about this research, I would like to brief a bit about what is a photocatalyst. Since I am from chemistry backgrounds, we have to know the definition of the photocatalyst. The photocatalyst is a substance which can modify the rate of reaction using the light radiations. Okay, in general, basically, the light as an energy source will be initiate the reactions or make the reaction faster. With the presence of the material, we call it as a photocatalyst. And this research we focus on water splitting reactions. Okay, this is the diagrams. What happens when we have a light and a material. We have a light initial reactions, light as energy source. Okay, we have a catalyst, a material. We call it a photocatalyst, and then we have a reaction to happen. Okay, the reaction will happen. So again, in my research currently, we focus on water splitting reactions. This is a water splitting reaction at a glance. All right, so we have the titanium dioxide as a very common photocatalyst exposed to UV, okay, the UV light, and then we have the generation of electron and positive hole. So this positive will oxidize the water molecule, okay, the water. So and then to produce H plus, then to the H plus will reduce using the electron produced, okay, and then to produce hydrogen gas, okay, and then we collect this hydrogen gas in these water splitting reactions, and then for overall reaction, so we have a water as a hydrogen source, okay, so we expose to UV light with the presence of photocatalyst titanium dioxide in our case, so to produce hydrogen gas and oxygen. So basically, finally, we'll collect and measure the hydrogen gas produced in our reaction. But somehow, currently, the efficiency to generate hydrogen gas remain low. So that means the photocatalytic activity of common or current or commercial titanium dioxide is very low due to their low surface area. So we come up with the material that have at least one dimensions at the nanoscale size between 1 to 100 nanometer. So we focus on nanomaterial. This is a general introduction about the nanomaterial. So the size is within 1 to 100 nanometer. So we can have here a few examples. We have a carbon nanotubes, okay, single wall carbon nanotube. We have nanoparticle. The House mole is a nanoparticle compared to N or to compare to with our strand of hair. So this you can imagine House mole this a nanomaterial, okay. So that's why we are interested to this nanomaterial study. And then for your informations, the nanomaterial can come with a few shapes, all right? So depending on their dimension, we have a 0 nanostructure, some we call it a nanoparticle. So we have 1D nanostructured materials. For example, we have nanorods, nanowires, and nanotubes. We have a 2D nanostructures material in thin film or plates or sheet forms, and 3D nanostructured material in bulk forms. Okay. In our research, we focus on 1D nanostructures material, which is a nanotubes. Okay, why we interested in this these shapes of nanomaterial? Okay, here we can see here we have 1D, we have nanofibers, nanotubes. Okay, in 1D we have spherical shapes. Okay, so for 2D we have a thin film or sheet shapes, and then for 3D they come up with a bulk shapes. Okay, we call interconnected and architecture materials. So why we focus on 1D nanostructure material, which is a nanotubes. They have a large surface area and pore volumes. You just imagine they have come up with so hollow elongated nanostructures, nanotubes. So they can provide large surface area and pore volumes, large fraction of surface atom, and then sometimes you can reduce the imperfections in order to come out with the best photocatalytic activity. And then for your informations, titanium dioxide has been used in various applications. Dioxide in photocatalysis. Okay, in commercially, the titanium dioxide has been used in food industries, in cosmetic industry and bakery industry. So that's mean the toxicity of titanium dioxide is very low. So we have tried to use environmental friendly material. So we select titanium dioxide. So how we prepare titanium dioxide nanotubes in our research? Okay, we use a hydrothermal method. Okay, so we have a commercial TiO2 mixed with sodium dioxide and then put in autoclave with the presence of 100 ml sodium dioxide, and then the mixture will be put in the furnace, okay, for 24 hours. Cl and distilled water, and then dry at 80 degrees C. Okay, so and then finally the product will be calcined at 300, 400, 500, 700 degrees C for 24 hours. Okay, and then the product will be characterized using SRD and TEM to confirm the formation of nanotubes as well as titanium dioxide. And then the product will be tested for hydrogen gas production. Okay, so very straightforward reactions. We have our photocatalyst, size photocatalyst, and then we have water. Since you use water splitting reactions, okay, so we mix together and then expose to UV light for 5 hours, and then we collect. For every 1 hour, we measure the hydrogen gas produced using hydrogen gas detector. For result and discussion, we characterize the commercials, the raw material of titanium dioxide. Okay, we have a raw material commercially obtained TiO2 precursor. We have a 160 nanometer, the size, and then this is the shapes of the commercial TiO2, and then we study the EDX, elemental analysis. We can only observe titanium and oxygen element in the sample, of course, since this is the commercial TiO2. And then the product obtains after the reactions, hydrothermal reactions, we have at 300 degrees C, 400, 500, and 700. All right, so using the SRD analysis, we can claim that at 300 degrees C after the calcination, we can obtain hydrogen tetride titanates. Okay, so, and then after 400 calcination, and then at that time we can observe, okay, can obtain the formation of anatase titanium dioxide, anatase TiO2. Okay, so this is the TEM image and EDX analysis of the sample after calcinations. We can observe the formation of hollow elongated nanotube structures. Okay, very good nanotubes with the diameter of nanotubes around 6 nanometer. Okay, so here we can calculate the diameter of the nanotubes. So, and then the EDX analysis, we observe titaniums around 60%, and then we have oxygen for 40%. And then we come out the mechanism how the titanium dioxide, the commercially transformed into titanium dioxide nanotubes. Okay, this is the reactions. So the commercial TiO2 react with sodium hydroxide during the hydrothermal reactions to produce sodium trititanates. All right, and then using the washing with HCl, acid hydrochloric, so we can observe the formation of hydrogen trititanate nanotubes. Okay, so the explanation we can observe here. The hydrogen deficiency on the surface layer can provide the driving force, surface tension for the pulling off the titanate layer, and the resulting the layer bend to form nanotube morphology. Okay, so and then this is the calcinations. When we come up with calcinations, the hydrogen trititanate nanotubes remains in hydrogen titanate nanotube after calcination at 300 degrees C. So we can observe the thermally stable of titanate after 300 degrees C calcinations. So that is why we have to increase the calcination temperature to 400, 500, and 700 in order to obtain titanium dioxide nanotubes. Okay, which is our aim, our target in this experiment. So here we can observe the equation. The hydrogen tetride titanate we convert to transform into titanium dioxide nanotubes at 400 degrees C, and then somehow after we calcine at higher temperature, so the morphology, we can observe the mixture of nanotubes and nanoparticle of titanium dioxide at 500 degrees C. And then after calcination at 700 degrees C in this study, we can obtain 100% of titanium dioxide nanoparticle. So that's mean the nanotubes of the sample we transform into nanoparticle due to the heatings at higher calcination temperature. So we carry out the surface analysis, okay, of the synthesized sample. So using the BET analysis, okay, for titanium dioxide precursor, the commercial we observe 9.82 meter square per grams for commercial TiO2. So for titanium dioxide nanotube, which is sample we obtain after calcination at 400 degrees C, the surface area is 226.62 meters square per gram. So as mentioned earlier, due to their hollow elongated nanotubes morphology, they possesses high surface area, which is more than 200 meters square per gram. So for the sample of the calcination at 500 degrees C, which we have the titanium dioxide nanotube mixed with nanoparticle. That means that nanotube is almost collapsed to produce a nanoparticle. The surface area is 108.24 meters square of grams. So, and then for the sample of the calcination at 700 degrees C, which is the sample in nanoparticle forms, 100% titanium dioxide nanoparticle. The surface area obtained of the samples is 55.24 meters square per grams. All right, so we can conclude here the nanotubes, titanium dioxide nanotube forms give the highest surface area to 126.52%. Okay, sorry, to 104.52 meters square of gram. All right, so now we move on to the hydrogen gas productions activity using the synthesized photocatalyst, right, as shown in the figure. So we can observe that titanium dioxide nanotube produce the largest, the highest amount of hydrogen gas, around 80 micromole. Hydrogen was produced using titanium dioxide nanotubes. And secondly, we have a titanium nanotube mixed with a titanium dioxide nanoparticle, which is the sample of the calcination at 500 degrees C. So, and then the second one, around 50 micromole hydrogen gas produced using titanium dioxide nanoparticle, which is the sample of the calcination at 700 degrees C. And then last but not least, the hydrogen gas produced using TiO2 precursor, which is a commercial TiO2. They are managed to produce around 25 micromole of hydrogen gas. Okay.
So, Professor, last 5 minutes.
All right. Okay, we're almost there. And then as a conclusion, so basically in this research, we have successfully produced titanium dioxide nanotubes and other nanostructures of titanium dioxide nanomaterial. So we have characterized using analysis. The photocatalytic activity study shows that the titanium dioxide nanotube can produce 80 millimole of hydrogen gas after 5 hours water splitting reactions. And in fact, this titanium dioxide nanotube shows the best photocatalyst in this research. And then we have a few reference here has been used in this research. And then that's all from my part. Thank you very much. Over to you, Prof.
Okay, thank you very much. So we are ready for the questions. Do we have any questions? You can talk and ask questions. So you do not need to write down the questions. You can talk and any questions? So maybe I can ask one question. So when we compare this method, your method, with the other methods, are there any connection? Because I am not specialized on PV generation studies, but are there any differences between the produced materials efficiency? Because the efficiency of the materials are important in order to get much more energy. So the method which you use can be better to have much more efficiency, and can you make some discussion on that issue? Thank you.
All right, thank you, Prof, for your good questions. So in general, basically, the different method they are produced different material with different efficiency. All right, that's the basic theory. So for in my case, in this case, we focus on hydrothermal method because it is a very simple method to produce titanium dioxide nanotube powder forms using a commercial TiO2 in our research. So maybe some research they come out with the titanium dioxide using a sol gel method or co-precipitation method, and then they come out with also with a titanium dioxide nanotube. But of course, the efficiency or the photocatalytic activity of that material is different with our sample. That's my comment for your question, Prof. Thank you.
Thank you very much for this interesting talk. Are there any other questions, maybe suggestions? So, okay, as the session chairman of this session, I am now about to close this session. So after 10 minutes, we will have other plenary sessions. So we invite all of the speakers to the following sessions. Thank you very much, and I close this session. And I also welcome all of our guests to our university, at least in a virtual form, and hope to see you all physically after this pandemic cases. And good luck and good work. Thank you very much for your contribution.